Hi everyone, and welcome to class 19 of this course. For this course, for this class, and for the next class actually, we're going to build on everything we've learned so far, and we're not going to add tools to the toolkit that you have. Rather, we're going to think about what it is that we can use all the tools that we have for, okay? And so today, we have all the basics of multiple regression we may need, okay? There's nothing we need in addition to that. We're going to see for the last two classes different techniques you can use within the multiple regression model, but this is as far as we're going to go. But remember, we started with the simple regression model, and it's not just because we wanted to make it easier for exposition purposes. We started with the simple regression model because we really wanted to talk about the causal effect of X on Y. That is, even though when we extended this model to having multiple regressor, we were still interested only in the causal effect of a single X on Y. So in our last example, it was the single X was the share of import competition from China, and Y was the share of patents. It could be schooling on wages, and all the examples we've seen in this course. But really, again, this is the only thing we really care about. And we introduced other regressors, other variables, only because we were afraid of omitted variable bias. And so today we're going to look at this question of, is the model that we have the right one if we want to answer really what's the effect of X on Y? And this is something that we call model specification. That is, do I have the right model given that the answer I want to get is what's the causal effect of X on Y? So next, we're also going to consider a model specification for a different type of exercise, which is prediction. So we have a model. Remember that I can use my estimate to actually predict any Y given that I have an X. So this Y hat, this predicted Y that my model is going to give me once I estimated it, is going to be right on the spot. So possibly every now and then I'm going to predict exactly the right Y I actually observe in the data. And sometimes I'm going to be off. So some models are going to be better suited for predicting very well Y's. Given that I give you any X, I'm going to predict the exact Y. And some models are not going to be so great at it. And so that's the second part of this course. Okay. Again, we introduced the multiple regression model when we started talking about control variables. Okay? So we add regressors to our specification because we're afraid we may get omitted variable bias. Now, we call these variables control variables and not the main regressor if they follow two things. First, they are not the primary interest of what you're studying. Again, if I care about schooling on wages, I don't care about socioeconomic status, okay? I care about socioeconomic status of the parents only because that may be an omitted variable bias. And if it's an omitted variable bias and it's not in my regression and I don't have a control experiment that allows me to get a situation where expectation of UI given xi is 0, then the beta hat I'm going to get is not going to be the right value. Okay, it's not going to be the population beta that I'm hoping to estimate with my data. So that's precisely what we're going to do here. Understand what is the role of those control variables and what do they mean for the multiple regression assumptions. So remember in class 9, so that was the very beginning of the multiple regression talk that we started, we said we can extend the assumptions from the simple regression model by first extending the conditional mean assumption to be true for all x's. So in the simple regression model, we said expectation of ui given xi at the time, so that was the only x, should be 0. And then when we switched to the multiple regression assumption, that we added more variables, more regressors, we said expectation of ui given all the x's should be 0. So again, the conditional mean 0 assumption is an important one, because if you don't have that, then the beta hats you're going to estimate are actually going to be biased. Then we also talked about all the regressors and the dependent variable needed to be IIDs. That's something we discussed in the last lecture when we talked about the need for clustering. And of course, we said that large outliers should be unlikely for all x's, and that we shouldn't have perfect multicollinearity. That was actually an assumption that we added to the simple regression model assumptions. Remember, why do we have assumptions? What do assumptions mean? They mean if these hold, then a consequence of this being true is that all our OLS estimators are going to be unbiased and consistent, and all our beta hats are going to be jointly normally distributed in large samples. So why do I care? I care because when it comes to inferences, when it comes to making claims about whether the beta hats that you estimated are statistically different from 0, where we rely on the fact that if they are all jointly normally distributed, then we're going to be able to make inferences. But think back on this part here. Okay, think back on assumption 1. What this is saying is, all x's should be uncorrelated with ui, which is to say x1, so think of it in terms of schooling, shouldn't have an omitted variable bias. Then we added a second variable, socioeconomic status, and we said both schooling and socioeconomic status should be uncorrelated with the error term. What this means is every time you add a new regressor, well, you would need for all this to be true that this new regressor also doesn't suffer from omitted variable bias. Okay, so maybe socioeconomic status of parents has an omitted variable bias such that this variable would be correlated with the socioeconomic status of the parents and have an influence on wages today. Okay, so maybe we should control as well for the socioeconomic status of the grandparents. And you see how this may take you very far, because if with every control you're adding to your model, you actually have to be careful that this variable itself doesn't suffer from omitted variable bias, then it may become very complicated. So if it's complicated, then what should you do? Specifically, recall from class 9, we took this scenario where we said, so say x1 is randomly assigned. Say x1, your treatment variable of interest, is really coming from a randomized experiment. So you don't have to fear that expectation of ui given x1 is different from 0. Okay, you kind of know and expect that this assumption is actually true, is actually holding. But say that you don't have specific reason to believe that it's true for other regressors. That is, when you add a control variable, then the mean 0, the conditional mean 0 is no longer true, and you know that. Okay, so is there a trade-off here? Should you decide to exclude x2 so that you get this assumption, which again we said is true by construction here in this context? Or would you still want to include this control variable even though you know that now this assumption is not holding, so the assumption that this is 0 is no longer holding? Well, the answer to that depends on what you care about. if what you really care about is beta 1, so the effect of x on y, which I gave away already that that's what we really care about in this class, then the answer to this is no. If what you really care about is that indeed you get the true unbiased beta 1, and so that you can make inferences with respect to beta 1 hat, then you don't have to expect this to be true, and you can replace this assumption by a weaker one. And we're going to call this assumption the conditional mean independence. So here's the idea. The conditional mean independence means that expectation of ui conditional on all your regressors should be equal to the expectation of ui conditional on all your regressors, but the one for which you have a main interest. So this may be schooling, this may be Chinese import competition, and all the other types of treatment variable we cared about. Okay, so the only way by which this equality is going to hold is if the expectation of ui given x1 is 0, and then if it's the case, then these two expectations here, conditional expectations, are equal to each other. Then if you do have conditional mean independence, and then the other assumptions that I listed before are true, then beta 1 hat is going to be unbiased and consistent, which again means that provided that you have conditional mean independence, then you're going to be able to make inferences about the true value of beta 1 and whether or not it's significantly different from 0, which again is what we only care about, and that's why we started this course talking about the simple regression model and only the effect of x on y. Okay, this class is really about how x is impacting y, what's the partial effect of x on y, holding constant other variables, but not caring that much about the beta hats associated with these other variables, with these control variables. So this is to say that if I have conditional mean independence for my x1, well, it may be that all my other beta hats are not unbiased and consistent, and well, you're going to be okay with that. So let me explain this in a fashion that is a bit different. It may be that when you add control variables, then what used to be expectation of ui given x1 being 0 is no longer true. Having those new control variables means that this zero mean, conditional zero mean assumption is no longer true. But if this is not true only coming from x2 to xk and not x1, so not the treatment variable that we really care about, if this assumption is not true, is violated only because you included control variables, but it's not coming from x1, then you're in a good place. Because you're going to be able to make inferences about beta 1 hat the way we learned how. It also means that when we had a simple regression model and we had a case in which expectation of ui given x1, so given the treatment variable, wasn't 0, so namely when we had an omitted variable bias for the treatment variable we cared about, and we added control variables such that the omitted variable bias would somehow disappear. When we did this, what we did really is allowing for the expectation of ui given x1 to become 0, even if we cannot guarantee that expectation of ui given all the x's is going to be 0. Okay, so again, by adding control variables, you may get rid of expectation of ui given x1 being different from 0, so you may get rid of the omitted variable bias. This may be at the price of actually having that the conditional mean independence across all regressors is different from 0. But if you found the right control variables, such that you're getting rid of omitted variable bias, then you're in good place. Now you're going to be able to talk about beta 1 hat in the way you want to, okay? So again, if you add control variables and it gets rid of the omitted variable bias on beta 1, you're in a good place, okay? But of course, it doesn't mean that all your regressors are themselves going to be uncorrelated with the error term, so that you're not going to be able to talk a lot about these other betas. So in our case about schooling and wages, when we had a beta for the impact of the social economic status of the parents, well, you can read it. Stata is going to give you standard errors associated with them, and you're going to be able to make inferences about the impact of the social economic status of the parents. But the truth is, you probably shouldn't. And in a way, it's quite okay. That's because you only care about the effect of schooling on wages, and you don't really care about the value of a social economic status. You only care about knowing that you're controlling for it, that you're keeping constant the effect of socioeconomic status on wages, such that you're really only capturing the partial effect of schooling on wages. And so that's why we're talking about causal effect. I really only want the causal effect of schooling on wages. And so you want the specification that is going to give you this conditional mean independence. And, as we said, you never can be sure that you have all the regressors you need to get rid of any and all omitted variable bias. But if you have good reasons to believe that you included all the right variables, all the right control variables, such that you can capture this causal effect, then it's okay that your control variables themselves are correlated with the error term. Again, in practice, there's no way you're going to be certain that you control for all the right variables, and that's why in every context, what you would rather have is a context where you have a control experiment in which you can vary randomly the treatment variable. And so within the multiple regression model, you can never be sure that you have enough control variables. But again, you include control variables only such that you can get the causal effect of your main X on Y, and not so much because you want to know each and every single coefficient on all your control variables. So it also means that, say you want to control for ability or talent when you want to look at the effect of schooling on wages. Well, if you have something that is close to it, such that an IQ test, okay, you can use it as a proxy for ability or talent. So remember that ability or talent is going to be an omitted variable bias if you're looking at the effect of schooling on wage. Okay, this is because if you're more able, probably you're going to go longer for schooling. So this is going to be positively correlated with schooling, and probably if you're able, you're going to also be able on the job and make higher wages. Okay, so this is an omitted variable bias. You can probably never control for it because ability is really hard to actually observe. But if you have something that is a proxy and that is actually correlated with ability, such as the IQ test, then putting it in your regression, including it in your multiple regression model, in other words, controlling for IQ test results, is actually going to get you closer to a conditional mean independence. And so you'll be able to talk about the effect of schooling on wages, controlling for ability, even though you don't really exactly have abilities. What I'm getting at here is really why econometrics is an art and not a science. We have these assumptions that are mathematical assumptions, but they are just assumptions. You know what happens if they are violated, but you can never prove that they hold. Okay, you can never prove that you have the model for which the assumption, and now simply the conditional mean independence assumption, is actually holding. Okay, and so the way you're going to think about this as an economist who has a question of the type, what's the effect of X on Y, is you're going to hope that you build the right model. Do you have to write only one model? Not really. What you do usually is you're going to look at a set of models and see if they produce similar results for beta 1 hat. That is, you're going to run in Stata or in any other software, you're going to run several regressions in which your main independent variable of interest is going to be the same. So say schooling or whatever it is that you care about and its impact on Y. And you're going to change the control variables that you're going to use. First, you're going to show us what you're going to call a baseline specification. That's the specification, usually already a multiple regression model that has the minimum set of controls you think are needed to get a beta 1 hat that is respecting assumption 1, okay? And specifically the conditional mean independence. You're going to show us this baseline specification. Then what you're going to show us are different sets of the same regression, adding or amending the control variables in your data. Again, think about schooling and its effect on wage. First, you may think, well, I really have to control for ability. There's not a version of my work I want to show in which I'm abstracting from ability, okay? So maybe the very first regression you should run is wages on schoolings and IQ test, okay? That would be your baseline specification. Why? Because you know that if you omit ability, then by definition you're going to get a beta 1 that is biased, okay? You're so sure that ability is an omitted variable bias if you don't include it in your model that there's no point in you showing me a result in which ability is not included. But then you can start listing other variables, other control variables that may or may not be needed for you to achieve the conditional mean independence, but you're going to show me that actually adding those types of controls are not changing your main results, and your main results are going to be about beta 1. What set of variables should you include? What is reasonable? When can you say, I have added that many control variables so I know that I have the conditional mean independence satisfied? Really depends on the context and the data. And again, that's why this is an art and not a science. And this is again, because you can never prove that you respected the appropriate assumptions, okay? There's no way you can prove that. You know what happens if they fail. If you don't respect these assumptions, you know what you're going to get. And so you're doing your best to respect these assumptions, but there's no way you're going to prove you respected these assumptions. So let me show you what this means in an actual paper. So this is again the Nathan paper. You may remember this paper as being interested in how the share of slaves that were exported to several countries in the world in Africa had an impact on the GDP per capita of these countries in the year 2000. Okay, so the idea is, at the time, a lot of slaves were shipped away to slave in other countries, and this has had an impact up until the year 2000 and probably today on the GDP. Okay, So what Nathan is doing here, is independent variable of interest is the export, so the number of slaves exported starting in the 1400s over the area of this country. Why do you divide by the area of this country? Well, large countries are more likely to export a lot of people because, large countries should have more people in principle. And so this is what this is capturing. This is taking the log. The dependent variable itself is a log. So now you know that what you're going to get is the elasticity of the number of people over area shipped against change in GDP. So the interpretation is going to be in percentage here and in percentage there. And so each column here represent a different regression. So in Stata here, you have 6 regress commands. He regressed these equations 6 times, okay? And so the baseline specification is going to appear in column 1. In column 1, what you have is this independent variable, this dependent variable, and you have a colonizer fixed effect. So in column 1, you're only controlling for one thing, and that what was the colonizer of these African countries at the time. The idea, which is quite simple, is if I know that some countries are formerly colonized by the UK versus France, well, maybe the UK has a strong impact on GDP today, and so I really want to control for that in my baseline scenario. I have no reason of never controlling for it because I know that, what the UK brought to those countries is different from what France brought, and this may have an impact on GDP. So what they brought sometimes are some types of infrastructure or some types of laws that may still be in the laws today or that may still be in use in the case of infrastructure and are going to change GDP today in those countries. So the baseline specification is this. And so as this variable increases by 1%, GDP decreases by 11% in this case. Then you're going to look at different types of models. So in the second column here, I have the same independent and dependent variable. I'm still controlling for a fixed effect for the colonizer type, but I'm also going to control for other variables. So these variables are included here because somebody probably raised his hand the first time he showed this result and said, yes, but what if distance from equator matter? Or what if the lowest monthly rainfall matter? Or what if the average maximum humidity matter? And so on, or average minimum temperature. What's the idea? These may be omitted variable bias. So say in the case of coastline over area, it may be that countries that have larger coastlines, so think of it as larger access to the sea, are better able to export, okay? So if you're better able to export, well, that would be correlated with export of slaves by definition. If you're more likely to ship any good, well, you sadly may also be able to ship humans, okay? And that would still have an impact on today's GDP because you would be able, again, to trade more, and this would have a positive effect on your GDP, okay? So this is true of all these variables, and so what you see here is really that he included several specifications in which is going to add more control variables or sometimes omit some of them, okay? But that's what he does. And so in the end, when I'm in a conference or I'm seeing someone present a paper, the first thing I'm going to do is absolutely disregard all the control variables. I'll check them later to see whether they make sense. But I don't really care about the numbers there. I really care about checking that this value on this row here, on this line, is not moving too much. Why? Well, if the omitted variable is such that the true effect of x on y is 0, then it may be that this goes from being, somewhat large and significant to become 0. Why is it nice here? Well, it's pretty stable across specifications. That means that even if you add, you can list all the omitted variable bias you can think of, include them in your regression, and still get pretty much the same results across specification. What this is telling me is, again, he didn't prove that he included all the right omitted variable that may exist, but of all the omitted variable bias he could think of, he included them the best way he could, and still the beta hat one is somewhat the same across all specifications. This is going to tell me I should tend to trust this result, at least with respect to the control variables included. It may be, again, that there are other omitted variable bias that are not included here, and that would take this effect to 0, but of all the omitted variable bias you could think of, none of them are taking his results to 0, which is reassuring. Before we move on, I encourage you to play a game. So I'm going to ask a question, then you hit pause, try to get the answer to that question, and then I'll give the answer. Okay, so what do you think this data is using? Is it using cross-sectional variation, or is it using panel data? Hint to get the answer, try to look at the number of observations here. All right, so I'm assuming you hit pause, and I'm assuming now that you get the answer. Okay, so here, this is using only cross-sectional variation. Nathan is using each country once, so he's using about 50 countries in his data set. You see that in this specification, so these two specifications are the same, but for this one, it has less observations, so probably that this column is using a different types for one of these variables, for which he only has information for 42 countries. So he's observing each country only once at one time, and this time is the year 2000. Okay, so this is an example of a regression using cross-sectional data. One last thing about this table. So again, each column represents a different regression, a different model in which you would have different control variables, and our independent variable of interest is again in the top row. Something that is changing across specification is what is called the R squared. The R squared appears in the data output. We're going to see that in a bit. You may remember seeing it, and you may remember that we haven't talked about it so far. But just note that across specifications, this R squared is going to change. What this R squared represents is how well the model is predicting variance in Y, the variance in the GDP across country in the year 2000. So we're going to have a much more specific definition of what the R square is, but note that as I increase the number of variables in my models, R square tend to go up. Okay, so it goes from 0.51 to 0.80. We're going to say that R square is somewhere between 0 and 1. So what this is saying is, as I increase the number of variables, it would seem that, in this case at least, my R square is going up. And again, R square is going to be a measure of how well your model is predicting changes in Y. So that's what the rest of this lecture is going to be about. From the very first class, we started to talk about the effect of X on Y. That's what we call causal effect. That's really the main interest of this course, and it's going to continue being so for the rest of this class. But just note that you could also use your regression analysis for prediction. remember from, say, midterm 2, that I ask you to predict y using certain values of x. How do you do that? Well, first you retrieve your beta hat, your estimated betas, and then you plug values for x and predict some y that we're going to call y hat. If you want to predict accurately this y hat, the way you're going to do that is you're going to compare the y hat that your model is predicting against the y that you actually observe in the data, okay, the yi that you observe in the data. And so depending on the regressors that you're going to choose, you're going to see that you are predicting more or less accurately this yi given the y hat that your model is predicting. And again, your model is specified in the way you decided by including some regressors and leaving out some others. What we're going to study now is what is commonly used as a measure of predictive power, or something we also call goodness of fit, in a regression analysis. So remember, again, that this all part here, that is all your betas estimated times some x's, are going to give you y hat. Okay, so all this part here, but the residual part here, is giving you y hat. And again, this is something we had in midterm 2. I told you, hey, given that you have beta hat 1 for the probability of being employed, what's going on if age is 30? So put an x where age is 30. What you would give me is then some y hat, okay? Now, you could compare this y hat to the actual yi given that age is 30. And that's what we're going to use to see how well we are predicting. But for now, just note that yi, so the true value that you observe in the data, is a combination of what your model is going to predict, so that's this whole part here, plus the residual. In our simple linear regression case, remember that y hat is just our line itself. The distance between each data point, so each actual yi and our line, is the residual, okay? So I think you have that in you now. So again, just note that yi is just what your model is predicting plus what your model is not predicting, the residual. Now, let's consider a measure of the variation in the dependent variable. And specifically, let's call the total sum of squares the sum of the distance between each data point and the mean of that variable squared. That's a formula that kind of looks like the variance, except that you would have to divide it by 1 over n minus 1 here. But essentially, you can think of it as the variance of yi. It's not properly the variance of yi, but you know, it's fair if you think of it this way. And again, we're just going to define total sum of squares as the sum of the distance between each observation in your data set, or each observation in the population, if you have access to that, minus the mean of that variable. It turns out, using the expression I mentioned before, that you can decompose this total sum of squared between two components. So I said that yi is a combination of y hat, the part that your model is predicting, and the residuals, okay? So replace yi by y hat plus the residual, and note that you can actually express this expression here as a component which is linked to the prediction of your model, and a component which is precisely what your model is not predicting. This first part here, we're going to call it the explained sum of squares. Why are we talking about explained sum of squares? Well, again, this part here is coming from what your data, or what your model is predicting, okay? So y hat is everything in yi that you are actually predicting. On the other hand, the sum of squares residual, this part here, is precisely what your model is not predicting. So this R squared that I mentioned before in the Nathaniel table is just going to be a ratio. It's going to be the ratio of explained sum of squares on the total sum of squares, okay? So you have the expression here, and think of it intuitively. I'm saying yi as some sort of variance in the population, okay? So if I observe, or even in the sample, if I observe yi is going up and up and down around the y mean, the average of y. So this would be some sort of variance. So that's the variance that you observe. And then there's the variance that your model itself is going to explain. So this ratio here is really the sample variance of y hat on the sample variance of yi. To see this, again, you can divide both sides by n minus 1. And note that this expression here is actually equivalent to 1 minus the sum of squares residual over the total sum of squares. Again, this part didn't change, that's this. The sum of square residual is this expression right here. So what this is saying, and that's completely equivalent to this, is the part that is not explained by your model divided by the total sum of squares. Now, note that the explained sum of squares can never be bigger than the total sum of squares. If your model is predicting very accurately, such that every y hat that you're predicting corresponds to the exact yi, then this term may be just as large as this term, but the part of the model that you're actually explaining, so the part where you're right and not off, can never be bigger than the total sum of squared in what is the true data, okay? So your model has some predictive power. You can never predict more accurately than the actual data, all right? So again, this term here can be smaller or just as large as this term here, but it can never be larger. This means that R squared is bounded above by 1. Okay, if this term is just as large as this one, then I'm dividing one thing by the same thing, that's going to be 1. It's actually also bounded by 0. Say your model have 0 predictive power, so that you are always way off for any predicted y, then this term would be 0, and this term would be, some positive number. 0 over something positive is just going to be 0. So R squared is actually bounded between 0 and 1. You can see it here as well. So again, say your model is very well predicting your y hat are very predictive of what the true yi is, such that the sum of square residual is actually 0. Well, in that case, this is 0 over something positive, but this whole term here is 0, and now this is 1. Okay, so that's 1 over minus 0, that's just 1. On the other hand, if your model is way off and you're actually never predicting anything, then your sum of square residual can be 1, and that's going to be, your sum of square residual would be just as large as the total sum of squares, and so that would be 1, this whole term here would be 1, 1 minus 1 would give you 0. Let me say that again. Your sum of square residual, in a case where your model is really, really bad and you're doing an absolutely bad job at predicting the true value of yi, if it's the case, then the sum of square residual is going to be just as large as the total sum of squares. So this whole term here is going to be 1, in which case the value of r squared is going to be 1 minus 1, which is just 0. So that's why we're going to interpret r squared as the fraction of the variation in the dependent variable that is predicted by the regressors. Again, r squared is out of the total variation in the dependent variable that you can observe, how well your model is actually predicting that variance. So if r squared is 1, then your sum of square residual is 0. That's something we said as well. If r squared here is 1, the only way by which this could happen is if your sum of squares here is 0, in which case everything here is 0 and r squared is 1. That's the only way this could happen. It means that each of your predicted value y hat must be exactly equal to the observed yi. So you did a tremendous job at predicting y hat because I'm throwing you any x and you're predicting exactly the right y hat. So we're going to see that in the simple regression case, it means that all the observations are actually lining on the line of your sample regression line. If r squared is 0, then one consequence of this is that all your betas are themselves zeros. Okay, so it means that you did a very bad job and that actually none of your variables are correlated with y. This is a case where y hat is just equal to beta hat 0, which is just equal to the average. And so the explained sum of squared is just 0. These are two extreme cases that really never arise. Okay, so you always have some idea of at least some correlation between some x's and y. And so you're going to find cases in which your r squared may not be great, but it's going to give you something that is just different from 0. Conversely, having a case where r squared is 1 is really, really rare. This is because unless you have some sort of specific data in which all your yi, the observed yi, is actually already lying on the line, well, it's very unlikely that you're going to be able to predict all the variation in y. So let's see again in the simple regression case what this means. Again, we have our independent variable here, our dependent variable here. I estimated a beta hat 0 and a beta 1 hat, so that the beta hat 0 is giving me the intercept, beta hat 1 is giving me the slope. So think of this line as your y hat, okay? I give you an x and you're predicting a yi, all right? So the part that your model is explaining is all the part along this line. The part that your model is not explaining, that is the residual, are the distance between each point and the line. You see that in this case, the r squared is quite large. 0.82, when it can be at a maximum of 1, is really good. Now, let's take an example where r squared is actually smaller. Now, the line itself is actually the same. Your model is predicting just about the same y hat. It's just that the true yi's are actually, the variance of the true yi's is actually bigger for each x. You see how the residuals now are increasing. So the distance between each data point and the line is increasing. Again, you should think of the line as your y hat and each data point as the yi. So going back, we see that if the variance across conditional on each x is actually smaller, then your R squared is going to be larger than if the variance here is larger. Again, if you then start introducing more x's, then maybe you're going to be able to fit better each data point and have a higher predictive power. In case we have a single regressor, well, your R squared really depends on the variance in the data. If you have a single regressor, then your R squared is going to be smaller in a case where you have larger residuals. It turns out that if you have a single regressor, well, this R squared is just the correlation coefficient between X and Y. This is a fact that's interesting to know. As you're going to add more regressors to a regression, your R squared is very likely to rise, and specifically, there's no way it's going to go down. Think of it this way. Say you add a new regressor, let's call it xj, and the coefficient on that regression that you estimate is not statistically significant, and it's truly zero. So the impact of x on y, that's just zero. Well, this is not changing the predictive power of other betas. So say you had other betas that were actually significantly different from zero, that were actually contributing to predicting accurate y hat, then the sum of squared residual will remain the same as before. So it doesn't change anything if you're bringing an xj, which is just contributing zero in your model. Okay, so if your beta hat is zero, then I give you an xj, the contribution this has on your y hat is just zero. So it doesn't change the sum of square residual that you get by just adding xj. It's not changing it as compared to the same specification, but without xj. So in the end, your R squared will be identical. Conversely, if you add an xj that actually has an impact, so that your beta hat j is now different from zero and possibly statistically significant, then the sum of squared residual that you're going to get is going to be smaller. This is again because now you're predicting with more accuracy your y hat, and if your y hat is more accurate, then by definition the sum of square residual is going to go down. And so by definition again, your R squared must increase. So let's take a simpler example within the Nathan example, specifically because, and you don't really have to know that, but I just want to mention it. When I talked about the R squared in the table I presented you before from the Nathan regressions, having fixed effects is actually going to increase the R squared by a lot. You don't have to know why, but I just want to mention this because you may be surprised that now R squared are going to be much lower than what I mentioned before. All right, so say you run the log of GDP per capita in 2000 for each countries. We still have 52 countries on the log of slave export divided by land area. Then instead now I'm going to look at this line here, which is going to give me the R squared. The R squared in this case is 31%. What this is saying is that the variation in the log historical slave export per million square kilometer predicts about 31% of the variation in present day log GDP per capita between African countries. What does this mean? You have a model that is going to predict GDP per capita. Your X of interest is actually, so, you could talk about the elasticity here, and that's the impact of X on Y. So basically, as this is moving by 1%, this is moving by negative 11%. The idea being, if you exported more slaves in your country, today you're doing less good than other countries, anything else being constant. What the R square is telling you is, if I want to predict GDP per capita in an African country in the year 2000 with some accuracy, how would this model predict GDP per capita across countries, across African countries? The answer, you're going to predict about 31% of the variation across African countries using this model. Is it good? Is it bad? Well, it's probably not great. If you need to really predict accurately GDP, I wouldn't start by just using this variable. Okay, if you want to predict GDP next year in African countries, you may think about better ways and better models to actually predict GDP. So the R squared here is not a great number. Now say I add to this regression another, what is going to be a control variable. Specifically, I'm going to add the log of coastline. What happens to my R squared? Well, it's going up now. This is again coming from what we said before. If you add control variables, if you add regressors to your model, this is mechanically going to increase R squared, or at the very least, just keep it stable. Okay, so in this new model, you're actually predicting 38% of the variation in present-day GDP across African countries. So by adding a single variable, you're actually now predicting much better the GDP. And again, what do we mean by this 38% of variation? Well, there's some variation in GDP across African countries that you observe today. How much of this variation can your model itself explain? 38%. It means that about 60% of the variation of GDP across countries is not accounted for in your model. And again, that's probably okay because, you know, if you wanted to build a model that is going to predict GDP, say next year, you probably wouldn't start with the share of slave exported about 600 years ago. And that takes us to why we waited so long before we introduced R squared. When we care about causal effects, or in our case, how the exporting slave is changing current economic condition in African countries, we're really asking the question of what's the impact of X on Y. We're not really in the business of predicting Y itself. Okay, so if you're going to macroeconomics, maybe you're very interested in predicting GDP next year or next quarter, and if you want to predict that, what you're going to use is not this kind of variables. You're not going to use the share of a slave exported 600 years ago, okay? Why do we care? Well, we want to know the contribution that this incredible historical event and very sad historical event has had on today's GDP. Before this paper, well, it was really easy to say, well, you know, I don't really believe that this had an impact. It was so long ago. I don't see why GDP today would be impacted by something that happened 600 years ago. And so, you know, this was an important question to answer. But Nathan doesn't really care about the level of GDP per capita across African countries. His goal is not to tell you next year, here is exactly what the GDP per capita of each African country is going to look like. What he really cares about, it's again, the impact that slavery has had on today's economic performance. So to really take home what is this difference between predictive power and causal effect, imagine you want to predict whether it's raining outside. So what you want to know is, with the best prediction possible, whether or not it's raining. And so say that you're a child and you notice that every time your parents are taking an umbrella that morning, on that same day, it's actually raining. Well, we know why. parents have access to weather forecasts, and so the weather forecasts are going to tell them today it's going to rain. You should take your umbrella. So from the perspective of the child, from our perspective, knowing that your parents are taking an umbrella that morning means that you can predict it's going to rain with a very high accuracy, okay? With just about the same accuracy as what the weather forecast is. And so your prediction in that case is going to be very good. So you could think of a model in which you're going to say your dependent variable is going to be probability of rain, your independent variable is going to be a dummy variable, my parents took an umbrella. If you do so, then you're going to have a very high R squared. And again, that would be right. As a child, you're going to predict very accurately whether it's raining outside by just looking at your parents taking an umbrella. Now, does it mean that umbrella, my independent variable, has an impact on rain, my dependent variable? Of course not, okay? We know that just parents see the news, are taking an umbrella, and it's raining on that day. It doesn't mean that taking an umbrella causes the rain. We're in the business of understanding what is causing rain, okay? And we're not going to explain 100% of the days when it's raining. But if we find some variable, some independent variable that is going to actually explain partially when it rains and when it doesn't, then that's when we're doing our job. So again, the main difference between prediction and causal effect is we don't care about the highest possible prediction power. We don't care about predicting every single day whether it's going to rain. Rather, we really care about finding the determinants of rain, and specifically a determinant of rain. Here, what Nathan is doing, he wants a determinant of GDP per capita. And specifically, this determinant was a negative one. And so countries that had more slavery are doing today worse, are in worse economic condition that countries that actually had fewer slaves. Okay, so he cared about a determinant of GDP per capita today being slavery. He doesn't care at all about predicting as accurately as possible GDP per capita in African countries. That finishes our class 19. I'll see you around soon.